see a couple super solid solutions in here. So, and I see probably 80% of them that could use some work. So, just to let you guys know, so if you're feeling like you need to be part of the in-group, messing up a little bit was the way to go. So, obviously, if I asked this question to optimize over anything other than MSE, that could have been hard. So let's just fill that in, but I could have changed this to mean absolute error, which would have been kind of cool. So let's entertain that question in our mind just a little bit. It wouldn't be, the MLE or the MOM estimator would not be optimal with respect to mean absolute error. But if I just asked the question of how do the two estimators compare under that metric, that's a different thing. There might be another estimator out there that beats it. So we'll be thinking about that a little bit. Let me just draw the likelihood function. I'm going to at least draw some optimistic cases. So here's case 1. This is 0, 1. Let me not draw like that. Let me draw like this. That's a 1/2. In case 2. That would not happen. Okay, I'm trying to make it so it bumps right over here. So if it did bump over to the right-hand side of the 1/2, it wouldn't be super peaky. So if it were super peaky, there's no way the data was generated out of something with the restriction. So, but it could by chance kind of just bump up right there a little bit. So I'm just going to make that the max. Or this is the 1/2 line right here. So that's star p is equal to 1/2. So we can see that that's p is equal to 1/2 right in here, and that's some other bump. That's the max. Okay. If I were recording myself, I'd probably make that bump really huge over here, just to exemplify the point. But if it was really huge, I'd know data wasn't generated like that. I would say, no way, I wouldn't believe you. Okay, just real quickly, we've already worked out the MLE for this, taking the derivative, setting it equal to 0, take a logarithm of everything first, and it's not too hard. So we've worked through all of that. So the MOM estimator, this couldn't be too much easier. Xi over n is equal to p. So that's already an unbiased estimator. I did say a MOM estimator. You could have built a different MOM estimator and worked through the variance and solved for that. That'd be a function that you know at least real quickly. And you could work through it and you'd be using the sum of the xi squareds or the y squared in here. It's your sufficient statistic. And that's going to be beatable anyway.
Is it okay if instead of saying sum of xi, we just put y?
Yeah, sure. That's what I mean. So I better match my own notation. This is what you guys do to me on finals, is just start turning it into some other problem. Very good. I'll mark myself down a few points myself on this quiz. So we know that. We've got a MOM estimator, so it's just this thing. Same as some of the xi's, if we were doing the Bernoulli case like they've done in the homework. So this would probably be a decent estimator. So we just say p hat is equal to y over n. So that's pretty easy. And then we could do the MLE thing, where I take a logarithm of py, 1 minus p, n minus y. Take the derivative with respect to p, set it equal to 0, and then solve for p is equal to p hat. So everywhere I see the p in here in this equation, once I do the solve, then set it equal to p hat MLE. So, and we wind up with, in the unrestricted case, that p hat MLE is equal to y over n. So we've solved that equation, so I don't think I'll do it again right now. You should be really quick in these sort of things. So if you get asked a question like this, it's really just writing down the step and going, the solution is that. So if I were trying to be fast on an exam, I'd probably write that out and just write this down. And then if I had some extra time, I'd fill in the detail here. So I would do things where it's like the professor knows, I know if I'm able to do this. You know, I'm just saving 2 minutes or something like that, if even that. So you want to be able to do this quick. So if I did ask the question for part A, which is better with respect to MSE, you would say they're the same because they're the same estimators that you would get. I guess you could get really cheeky with this and build a different MOM estimator and then have to do lots of math to show which one is better. So, but if you're not using the sufficient statistic, i.e. the Y itself, the number of successes, you're going to blow it. So if you did use the variance estimator and solve for the y squared or something like that and have it in terms of y squared, you're using the wrong statistic. So, and you would be able to demonstrate that the MLE was better than that. So here's the restricted part right here. If I were doing the MLE on everything, I just need to look at where the maximum is. So this maximum would happen right here at y over n. That's where what we solve over here. So where does this function bump? The half restriction doesn't interfere with that. So it's still a maximum in the valid range right here. So you always have to adhere to the support of that parameter. The parameter lives between 0 and 1/2. And so for the MOM estimator, it doesn't matter. This is always the answer. And so if the case looked like this right here, where the maximum happened to bump right over to the right of 1/2, it wouldn't be realistic if it did this. So then the MLE doesn't have any support over here. So over in this bump right here. So the MLE is only defined where P can take on values. So if I tell you P lives between 0 and 1/2, and you report this back as an answer, that can't be the MLE because the maximum is actually here, right here. The likelihood function over on this side is 0. So it would be 0 now. So I can get rid of that stuff right here. So because that's the maximum in the support of the variable. And so the MOM estimator could possibly give me an estimate that doesn't adhere to the restriction. So that's one of the beauties of likelihood functions, is they're guaranteed to put the estimate in the valid range. And MOMs don't necessarily do that. So which one is better in terms of MSE? If we just write down the definition of MSE, MSE looks like this. I'll say over Y. This is just going to be P hat minus P squared. That's what MSE means, squared error. And then I'm just going to average with respect to the sampling distribution. That's just what this is. So this is going to be the expectation. Just write this down. Expectation of P hat minus P squared. So you can just work through this thing. So this is just sum of the y's. I don't really even care what this part is. I'm just going to leave that the same. Yes, David?
Could we say something like when the only time that the MOM estimator and the MLE will differ in the B scenario is when the MOM estimator is outside of the range, and in that case it must necessarily be further from P than the MLE.
Yeah.
And so
that's going to be the argument that we'll write down. Yeah, I think you wrote it right on your thing.
Well, I didn't say that because
Yeah, exactly. Yours is a little bit more elusive. I did see what you said. So it's leaning in that direction. So here's how I would like you to do it. So just take the MLE. So if we ended up looking at this picture right here, we know that the MLE in this case right here is the average, y over n. And the MLE in this case is just 1/2 right here, and it's bounded by that. So p hat MLE is equal to the minimum y over n in 1/2. So then this is the argument that David's going to make for us. So we just stare at this equation. When we think about what happens here, this is just going to be some y goes from 0 to, I'll say, up to y over n. I want to make sure that that's bounded by 1/2 right here. So this is going to be up to this such that this, I'll say, I'm going to write it like this, 1/2. What's the right way to write this? I'll do it like this. We'll work on this in a second. Fy given p plus whatever this thing is. I'll say p hat, this is either going to be mom or MLE, you can think of those two things, minus p fy given p right here. So I need to just come up with some notation to what I'm summing to. I don't want this thing to have a y such that y over n is bigger than 1/2. So I need some notation for that. So help me out real quickly.
Just write n over 2.
What's that?
Just write n over 2 and
Almost. So isn't there a case where I gotta be just a little bit careful? I guess that would work. So n over 2, but that's not in terms of y, right? So the notation's not super clear here. So I want to sum up to y. What's that?
Something or 1/2.
Yeah, right. So y over n is less than, what's that?
Y over 2n can be equal
Y over 2
when you take one.
You want to floor it?
Yeah.
Wait, why do you want the bound being inverse of y?
Because I'm summing over y. So, but I guess that's right. That's fine. So we could just do n over 2. I think that's right. So we're going to sum up to whatever that is, but we don't, this is still not right. Any other ideas?
Write in words.
What's that?
Write in words.
I think it should just be like less than n over 2.
Right, less than n over 2. So I kind of like that. I think that it's this, it's less than this. So that's the floor of that thing. I think this is what Saeed's saying too. So up to this thing right here. So, and then I'm going to go from this same value right here, I'll call that star, up to here. But this is basically the value where it exceeds 1/2 in this, that y over n exceeds y out 1/2. So I don't want to sum over that. Here's the key point, is that over on this side, right here, the mom and the MLE are both y over n. This is the exact same value right here. The only thing that happens is when I cross this threshold where y over n is greater than a half. So that's the break point we're looking for. That's my star. So this could either be y over n in the mom case or 1/2 in the MLE case. So those are my two different possibilities. And what we know is that our estimator is guaranteed to be, should be over here. So P is over here. And so all of these values that we're summing over for y over n are getting bigger and bigger than a half for the mom estimator. So it's drifting and tending away from a half. And so that's bigger. And so I just have to look at this part of the sum that the MLE is always closer to the true answer because over in this range right here, y over n is bigger than a half. So all I have to do is look at this part and argue, this is squared, that this thing is bigger for the mom estimator. And so you conclude that the MLE is the better estimator. I think that's what David tried to say in about 3 words. It took me about 100 or so. But that's really what's going on. So I didn't even have to do the bias variance decomposition. It seems very, very tempting to do it, but that's a lot of extra work. And I'd say at least half of you start going down that line, which is fine on the homework, but it might not be a great line of attack for a midterm. So all you have to do is just think about the general definition. If I had changed this to MAE, now granted, these aren't optimal estimators that we've come up with respect to the mean absolute error, but if I changed it to mean absolute error, these would just be absolute. Or whatever norm I picked, right there. And the same exact argument would hold. That y over n is getting bigger and bigger from anything that's less than a half, no matter what I've done here, just as long as that's a distance measure. So let me just ask a follow-up question, B3, if I wanted to make this a little bit more tricky. What would be the optimal estimator with respect to mean absolute error? Dylan?
Yeah, something to do with the median probably.
Yeah.
I don't know, like median over n or something?
It's the median.
Just the median.
It's just the median. Yeah. So the median is kind of in the middle, close to x bar maybe. So, you know, dividing it by n, the median would throw it all the way to the left. So you could use the same argument, but if I wanted to make this question a little bit trickier, then I might say, show me which one is better with respect to MAE, and then I would do a follow-up question and say, now derive what the best estimator is with respect to MAE. And you would want to be able to do some other proof to show what that optimal estimator is. So if you want a homework problem that will fill in that blank, it's 713 in the book. It's not exactly written in terms of this problem, but in disguise it is this problem. David?
Yeah, so for, this would be the mean of observations from Bernoulli distribution. And so if the median, that would have to be either 0 or 1, or maybe 1/2 in a few cases. But how could, is the median still going to be optimal there?
With respect to MAE, yeah, it's kind of a weird thing.
Like just estimating, if we have more zeros, it's 0. If we have more ones, it's 1.
I suppose that would be the NAP estimator, the 0-1 loss estimator. So yeah, that is a little bit funky. So maybe it's a good thing I didn't ask that question because you'd have to go through a lot of work.
I think,
But I could still ask this same question about which one is better. So which estimator is better? And I think that would be a reasonable question. So sometimes it is, sometimes I make a question too hard unintentionally. So that would have been a hard question if I asked it for Bernoulli. Exactly.
I think what David's trying to say is like, with this particular example,
Yeah.
you've got one sample.
Yeah.
So
Right,
what's
right. I get
the
it.
kind of median there?
Yeah, I got his point. Yeah, this would be really hard in this example. So I probably wouldn't give a problem like that for this. So anyway, I could still ask the question without doing the B3 muck-up. So I didn't ask that question, thank goodness. But which one is better with respect to MAE? And you can still answer the question. So that's what chapter 7 is all about. Deriving two estimators, different techniques, and then comparing them. And that's it. So that's what 7 is all about. Are there any other estimators out there that are better than the estimators that maybe you found? And so we could be thinking about this question, oh my goodness, if I change the norm, what would be the optimal estimator? So, and how would I show that it beats some other estimator? Sometimes we have some theory up front where we just know the answer, that this is unbeatable. And that's where we're going to be getting with Ravel equalization and Kramer-Ravel. And we're going to kind of skip over all the Lehman-Sheffey stuff that they put in the book. Anyway, I think this is good practice. So just know that there's easy ways through problems and hard ways through problems. So have a couple different tools and think about these problems carefully. We'll meet again on Thursday to do this and go through all of those details before the midterm. So again, on this, I'm just going to write down attendance, see how you did, just kind of mentally know where you're at with everything and look for improvement. So I think that's the goal. Okay. Thanks for your patience on that. I want to do invariance of the MLE, but I also just want to recap what we've done with EM and then close the lecture series on EM and just have you code this up. So you're going to be coding this up. There's a simulation assignment that's on the web, so have a look at that. What you're going to do right here for in your EM algorithm, when you code it up, really you're just coding up these two steps. That's it. So we've already derived the Q function, so you're not doing anything crazy in your for loop with that. So what you're going to be coding up is just these probabilities right here. So for each one of these xi's right here, there's n of them. I'm going to have a little sub for loop in here. I goes from 1 to n. And I'm just going to compute these probabilities right here. Pi I k in iteration t, which is my outer loop. And this is just going to be e to the minus 1/2 xi minus mu k squared over sum k goes from 1 to cap k e to the minus 1/2 xi minus mu k squared. I've forgotten all my variances. Variance under there, sigma k variance. I'm going to need these. 1 over sigma k t. And this is going to be 1 over sigma k t as well. And then I'm going to have these priors also. So I'm going to have my pi k right here. So I'll just say probability that ci is equal to k. Probability that ci is equal to k. There's a couple different choices that you could pick for these things right here. You could pick this as 1 over cap k, or you could maybe pick it as the MLE estimate from step 2 in this algorithm. So David Hines asked a question last time about, you said that these algorithms are the same no matter how I pick this. If I use the MLE estimate, pi k in the previous iteration right here, and I misspoke. They're not the same. They're very close to each other. So it won't make a tremendous difference. So as long as you're using diffuse priors, basically if you have a lot of data, that's what's going to take over the inference, and it's not going to be your priors. If I have really strong priors on things, that are biasing things, I can come up with different answers. So my point is that the uniform priors are pretty loose diffuse prior. And so if I have a reasonable amount of data points, I should be coming up with the same answer because they're both reasonable priors, relatively diffused. So, but they're not exactly the same. So my guess is you'll be off just by a smidgen if you do it 2 different ways. So you're also going to have a for loop here on k. So 4k goes from 1 to cap k. So you just have this double for loop computing all of these probabilities for you. That's all you're doing. So for each one of the i's, you're coming up with all of these and you're loading those things up. So now you've got all these probability weights, and it's basically just measuring, oh, and I should probably throw some t's on all of this. T there. I've got t's here, t's on all my variance estimates, t's on all my mean estimates. So you're going to have to initialize the first time through this loop to compute all of this, so there's a 0th step to this algorithm. And then you're going to update these theta. So what I mean is your means are going to look like this. Sum of the xi's over pi ik divided by sum of the pi ik's. This is at my tth iteration. Or I should probably say my t plus first iteration. I guess I call them t's right here. I guess that's okay. So I'll just call them t's. Sigma is just going to be, I'll say sigma squared is just going to be the sum of the xi's minus mu k t. So these things. Get that right. Plus 1. Pretty clumsy notation.
Is that one? Change to equal?
Huh?
Just the pi ik change to equal.
I guess I'd call these t's right here. If you'd like, let me do this. Plus 1, plus 1 for those. So my recently updated ones, and I would have these as plus 1s. Then that would be a plus 1. Just depends on how you've indexed it. So this is going to be plus 1. Oh, you're asking about that one. Yeah, you're going to use your most recent one, squared times pi ik t plus 1 over sum of the pi ik's t plus 1. You might ask about updating the actual pi's themselves. The whole pi, you don't actually need to do it if you're using the uniform prior. If obviously you're using these right here, from your previous step, you need to compute these. And it's just the average of your pi ik's, like we derived last time. So if you don't want to use those and you want to use the uniform prior, you're just updating those. If you're doing this in high dimension, you're not going to be squaring things here, you're going to be using the outer product, but it's going to be the exact same form. So really, what is there to code up on this assignment? It's you need to run the forward simulator, so you simulate out of the mixture model. You'll know what the answers are because you'll pick mu's, you'll pick the sigmas, you'll pick the pi's, and then you're going to run EM to try to get those mu's, sigmas, and pi's back. So and you're just going to do that for a couple different examples. So really, this is pretty easy to code up. Probably the hard part is remembering what the proof looks like. So I'll just say it right now so you can focus on your studying. No proof on EM on midterm 2. So I'm not going to ask you for a proof of it. I'm just going to ask you maybe some questions of if you know how it works. So this is all your coding in.
For like initial values, we should obviously like pick something that
Yeah.
makes sense, right? Like they shouldn't say the same.
Probably not amps, probably not bands. So probably not extreme crazy values. What would I normally do? Probably run k-means up front and initialize everything with that.
So this, I guess, assume, like the notation you've done, it assumes that you'll update first the pi ik,
Yeah.
then the mu.
I just made an arbitrary choice. I could have updated them in the other order.
Yeah.
It's up to you. So you pick which direction. I guess in my mind, when I was indexing, I had already updated the pi's in my mind.
Is there a reason to choose in particular order?
No, if it makes a difference, you're host. So anyway, no, there's no great reason to choose what you update first.
So we're picking some values of the original mu's and sigmas.
That's right.
So don't initialize them as what we originally picked, or
don't initialize them using the true answer. So don't do that. What I would do in practice is probably run k-means. So then I'd have some different groups on things. It could go horribly wrong if my variances aren't close to each other. So, but it gives me some semblance of an answer. I come up with something, I pick the centroid values for each one of my groups and I plug them in. Is my mu's, I compute the variance for all of my groups, and that gives me my variance or my covariance estimates, and then I just go to town. So that's how I probably do it in practice. But if you want to just start with anything crazy, and when I usually code this stuff up, I want to make sure my code works under crazy inputs. And so I like to stress the code with, let's just let the probabilities on everything just be uniform. So, or I come up with just some random assignments to each one of the different xi's. I just assign them to groups, then I can compute some means up front, some variances. I've got my initial estimates for my probabilities, and I just go to town. So I usually try to initialize everything very randomly just to stress my code.
So we might try having specifying n to be larger than the number of actual normals.
Yeah.
There's a few ways to express the mixture.
Do sensible things. So if you want to pick n to be much, much smaller than the number of parameters, don't be surprised when it doesn't work very well.
I'm just saying, I was thinking the other way, is pick n larger.
Obviously. Yeah, probably. Do reasonable things. So, but if you want to show the limits, it doesn't work very well if you have too many parameters and not enough data. You can show that in your sim study. So EM's everything will not work well in that case. So you pick some choices, just make some choices and see how it works. Pick choices where it works really well, choices where it doesn't work well.
And then are we doing some write-up on this again?
Yeah. Okay. It's going to be much shorter. Cool. That's it. Let's do invariance of the MLE, just real quick. So I'm just going to say if theta hat is the MLE with likelihood theta, and I'll just write down likelihood theta and be really clear about this. So how did I get that right there? This is just the arc maximum over theta, and that's theta hat. So, and I want to entertain a function of this. I'm going to say eta is equal to g theta. Then eta MLE is equal to g theta hat. I'll call this the MLE. So it just means if you got the MLE and you want to transform it to a different scale, you just transform it directly, which is kind of cool. That doesn't happen with mom estimators. You can just think about Jensen's inequality. If I were looking for something and the estimator was X bar, you know, and that was the mom estimator, if I flip that thing over, 1 over X bar might not be unbiased. So if X bar is unbiased, 1 over X bar is not unbiased. How do you know? There's only one word that I need. One word. So where are you leaning? Yeah, you're right. That's a word.
You said Jensen.
Jensen's. It's Jensen's. So just use Jensen's to show you that you break all the properties once you start transforming things. It's the point that I never got about the unbiased argument. Then you transform it and it's now biased. So if you liked unbiasedness to begin with, what the heck? So, but MLEs kind of have a really nice property. Let's just look at the proof. Just a quick proof of this. This just says if I'm maximizing over eta, and I have a likelihood function written down in terms of this parameter eta, if I can write down that G, I'll just say, G theta is equal to eta, and eta, I'll say G inverse eta is equal to theta. So if 1 to 1, I can end up writing this down. So we can write this. And it maps back to just one value. So if I do that, what I could end up doing is I could end up just writing down another maximization problem. And I can maximize this over eta, and I can end up using the likelihood for theta and plugging this thing in, G inverse eta. What I don't like about this proof is that they use a star instead of these symbols in the book. It really is the same function. So that's what I don't love about the proof, because the function is identical. Same thing happened in the likelihood principle sort of stuff. So I try to clarify some of that notation. One thing I can do is I can either think about this as all of theta. So I could either turn this thing and start searching over the whole entire thing of this, or I could search over etas. And when I move eta, effectively I change G inverse, because it's a function of eta. And so I could still maximize over that right there, and this is going to be the same as the maximization over theta, likelihood theta, over x, where this is the likelihood function. Let me just show you real quickly why this proof is obvious through an example and what's going on. The non-one-to-one case, the result is still the same. We just need a slightly different definition on how we maximize over theta space. And I'll tell you what that is next time. But just as a quick example, let's just look at if I had a likelihood function that looked like this. I'll say v to the minus n over 2 e to the minus xi squared over, rewrite that, minus 1/2 sum of the xi squareds over v. So if I just had some crazy function that looked like this, and I were trying to optimize over this, I could maybe find the answer. This is a normal distribution with 0 mean. So I'm just looking at the variance. So v is variance right here. So this is just a normal with the mean is equal to 0, and I've got some free parameter v. So the variance. So let's say I ended up maximizing over this. So I'm going to get the R maximum over v, v to the minus n over 2, e to the minus 1/2 sum of the xi squared over v. Let's say I just came up with some answer. I'll call it v hat. And I'm going to say that number is 5. Let's just say I know what the number is. And give me something that I can just kind of work with. Let's say I transform. Consider the transformation. Phi is equal to 1 over v. This is called the precision. So 1 over the variance is the precision. So if the variance is large, the precision is low. So if the variance is really small, the precision is high. So two different ways of thinking about the exact same thing. And I just re-encoded this right here. So I'll call this likelihood v, and I write down likelihood phi. And all of my data, all I'm going to change is just this stuff right here. This is going to be phi to the n over 2, e to the minus 1/2 sum of the xi's squared, and I'll put my phi up here. The question is how would I maximize this function? I know a few things about this right here. So I could just think of this as v inverse, if you'd like, which is phi. So it looks just like that thing, right there. What do I need this thing to be right here? I need this thing to not be 5. I need it to be something different for this to take on its optimal value. Let me just rewrite this right here. V inverse. So if I just rewrite it that way, it's the exact same equation. I haven't changed anything. I don't want that to be 5. I want it to be something different. What would I pick V inverse to be? Huh?
101.
Yeah, 0.2. So I want that to be 1 over 5. 0.2 right here. So, and it's the exact same function. It's the exact same thing. So I really need this also to just be 0.2, which would be the exact same thing as if I picked V to be 5. It's the same function that I'm optimizing, so I just need the V in there to be 5, and V inverse would be 0.2, and it would be equivalent if you just solve that equation. So there's really not a lot to think about with that result. It just is. That's the way transforming things works. Keep in mind, when I transform a likelihood function, I don't have the Jacobian appearing. If I did have the Jacobian appear in things, that might not necessarily transform just the way you think it does. So the Bayesian map, the maximum a posterior estimate, doesn't enjoy this property because of the Jacobian. But likelihoods are just functions over these parameters. So I'm not thinking about the stretch on everything and integrating over them. It's just a function that I write down. So it's really just kind of an obvious result. This is true for any optimization problem. This wasn't special about likelihoods. This has always been true. So you find the maximum under one parameterization. In the one-to-one case, at least, we have a proof right here that says just take the transformation over the other thing and it'll maximize the other function. So easy peasy.
If it's not a one-to-one case, and let's say 2 different values of eta map to the same value of theta, then you would have 2 values of eta that are that value.
Yeah, so all you do is you take the one that maximizes it. So plug both of those values in and take the maximum over that set. And that's what you do, and that's the auxiliary proof for the non-one-to-one case. So what you do is if it maps back to 2 values or a set of values, figure out which one is the best one. So, and we just need a definition for that, and I'll write down the definition next time of what that means mathematically. But you just take the one that maximizes the likelihood out of those 2 values.
If G is equals 1 though, then the eta are not a parameterization for your variable, are they?
What's that?
If G is not 1-to-1, then eta can't be a parameterization for your variable, right?
I take the maximum one. I have to reduce the set to one of the picks that is not 1 over. But the result is still true. Anyway, read through the book. Let's come back on Monday, just catch that last little point up. So, but basically I just maximize over the sets of eta that it's mapping back to. And that's my new definition of my maximum likelihood. What else would it be? So I want to maximize things, so you pick the one that's best. That's it for now, you guys. Thank you very much for your patience with time and with the quiz. I think it'll help us out with the midterm. I think we'll do maybe one more quiz next week. Would that be helpful? It's up to you guys.
Yes. Maybe.
Say yes. I say yes.